Electrical theory discussions can become confusing when intermixed with code requirements. A dedicated section for electrical theory could provide clarity. This separation would allow for exploration of electrical concepts without the constraints of specific code mandates. It would also help differentiate between established code regulations and theoretical ideas being discussed. This distinction is important because code requirements are legally binding and must be followed for safety and compliance. Theoretical discussions, on the other hand, can explore new ideas, challenge existing assumptions, and contribute to a deeper understanding of electrical phenomena. The key is to distinguish between the two. When discussing specific installations or designs, it is crucial to adhere to the relevant electrical codes, such as the National Electrical Code or NEC in the United States. The NEC provides comprehensive guidelines for safe electrical installations. It covers aspects such as wiring methods, overcurrent protection, grounding, and equipment installation. When discussing theoretical concepts, it's important to acknowledge that these ideas may not be directly applicable to real-world installations. They might be based on simplified models, idealized conditions, or hypothetical scenarios. Theoretical discussions can explore the behavior of circuits under different conditions, the effects of various parameters, or the potential for new technologies. However, it is essential to recognize the limitations of these discussions and to avoid applying them directly to practical situations without proper consideration of code requirements and safety standards. For instance, consider a discussion about the efficiency of different types of transformers. Theoretically, one type of transformer might appear to be more efficient based on certain calculations. However, in a real-world application, factors such as load variations, operating temperature, and harmonic distortion could significantly affect the actual efficiency. Therefore, it's important to consider these practical factors and to consult the relevant codes and standards before making any decisions about transformer selection. Another example is the discussion of grounding and bonding. Grounding is connecting to the earth. Bonding is connecting metal components together. Electrical theory explains the principles behind grounding and bonding. These principles are there to protect people from electrical shock and to provide a path for fault current to flow back to the source. However, the specific methods and requirements for grounding and bonding are detailed in the electrical code. Therefore, a theoretical understanding of grounding and bonding is essential, but it must be complemented by a thorough knowledge of the code requirements. Clear communication is crucial to avoid confusion. It helps ensure that everyone is on the same page regarding the applicable codes and the theoretical concepts. Use precise language, avoid ambiguous terms, and provide clear explanations. Cite specific code sections when discussing code requirements, and clearly state when you are discussing theoretical concepts. Encourage questions and discussions, but always emphasize the importance of adhering to the code when working on electrical installations. The grounding electrode conductor, or GEC, connects the grounding electrode system to the electrical system's grounded conductor, typically the neutral busbar in the main service panel. Its size is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The GEC ensures a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The equipment grounding conductor, or EG, connects the non-current carrying metal parts of electrical equipment to the grounding system. This includes metal enclosures, conduit, and equipment frames. The EGEC provides a path for fault current to flow back to the source, preventing dangerous voltage build-up on metal parts that could pose a shock hazard. The size of the EGC is determined by the rating of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. Understanding how to properly size the GEC and EGC is crucial for ensuring electrical safety and compliance with the NEC. The properly sized grounding conductors can compromise the effectiveness of the grounding system and increase the risk of electrical shock or fire. Bonding is the process of connecting all non-current carrying metal parts of an electrical system together to create a continuous electrical path. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of voltage differences that could cause electric shock. Bonding is particularly important in areas where water or moisture may be present, such as bathrooms, kitchens, and outdoor locations. The NEC specifies detailed requirements for bonding different types of metal components, including metal water pipes, gas pipes, and structural steel. Grounding and bonding work together to provide a comprehensive electrical safety system. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts are at the same electrical potential. By properly grounding and bonding an electrical system, you can significantly reduce the risk of electrical shock, fire, and equipment damage. The NEC provides detailed guidance on how to properly ground and bond electrical systems, covering various aspects such as conductor sizing, installation methods, and bonding techniques. In addition to the grounding electrode conductor, or GEC, and equipment grounding conductor, or EG, other types of grounding conductors are used in specific applications. One example is the supply-side bonding jumper, which is used to connect the grounded conductor to the equipment grounding conductor at the service equipment. The supply-side bonding jumper ensures a low-impedance path for fault current to flow back to the source in the event of a ground fault on the supply side of the service equipment. Another example is the main bonding jumper, which is used to connect the equipment grounding conductor to the grounded conductor at the separately derived system, such as a generator or transformer. The main bonding jumper serves the same purpose as the supply-side bonding jumper, providing a low-impedance path for fault current to flow back to the source in the event of a ground fault on the separately derived system. When working with electrical systems, it's important to understand the purpose and function of each type of grounding conductor and to ensure that they are properly sized and installed according to the NEC. Improperly installed grounding conductors can compromise the safety and performance of the electrical system. Overcurrent protection is a critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can cause overheating, damage to equipment, and even fire. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when a fault or overload condition is detected. Fuses are one-time devices that melt and break the circuit when subjected to excessive current. The NEC specifies detailed requirements for overcurrent protection, including the types of overcurrent protective devices that are permitted in different applications, the ampacity of conductors, and the interrupting rating of overcurrent protective devices. It's important to select overcurrent protective devices with the appropriate ampacity and interrupting rating for the circuit being protected. An overcurrent protective device with too low of an ampacity will trip or blow unnecessarily, while an overcurrent protective device with too low of an interrupting rating may not be able to safely interrupt a high fault current. The interrupting rating of an overcurrent protective device is the maximum fault current that the device can safely interrupt without being damaged or causing a hazard. The interrupting rating must be higher than the available fault current at the point of installation. Available fault current is the amount of current that would flow in a circuit during a short circuit condition. The available fault current can be calculated using various methods, including short circuit studies and point-to-point calculations. It's important to determine the available fault current before selecting overcurrent protective devices to ensure that they have an adequate interrupting rating. The NEC requires that overcurrent protective devices be readily accessible and properly labeled. This allows electricians and other qualified personnel to quickly identify and operate the devices in the event of a fault or overload condition. Overcurrent protective devices should also be regularly inspected and tested to ensure that they are functioning properly. Electrical panels are distribution points for electrical circuits within a building. Electrical panels typically contain circuit breakers or fuses that protect the individual circuits from overcurrent conditions. Electrical panels are available in various sizes and configurations to accommodate different electrical loads and applications. The NEC specifies detailed requirements for the installation of electrical panels, including clearance requirements, wiring methods, and grounding requirements. Electrical panels must be installed in a dry, well-ventilated location and must be readily accessible for inspection and maintenance. The panel must be properly grounded to provide a path for fault current to flow back to the source. The circuits within the panel must be properly labeled to indicate the loads they serve. When installing or working on electrical panels, it's important to follow all applicable codes and safety precautions. Working with electricity can be dangerous, and it's essential to take the necessary steps to protect yourself from electrical shock and other hazards. Wiring methods refer to the ways in which electrical conductors are installed and protected. The NEC recognizes various wiring methods, each with its own specific requirements and applications. Some common wiring methods include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IM, flexible metal conduit, or FMC, non-metallic sheath cable, or NM cable, and underground feeder, or UF cable. Rigid metal conduit, or RMC, is a heavy-duty steel conduit that provides excellent protection for electrical conductors. RMC is typically used in industrial and commercial applications where mechanical protection is required. Intermediate metal conduit, or IMC, is a lighter weight steel conduit that offers similar protection to RMC but is easier to install. Electrical metallic tubing, or IMT, is a thin-walled steel conduit that is commonly used in residential and commercial applications. EMT is lightweight and easy to bend, making it a popular choice for many electrical installations. Flexible metal conduit, or FMC, is a flexible metal conduit that is used to protect electrical conductors in locations where flexibility is required. FMC is often used to connect motors, appliances, and other equipment that may be subject to vibration or movement. Non-metallic sheath cable, or NM cable, is a type of cable that consists of two or more insulated conductors enclosed in a non-metallic sheath. NM cable is commonly used in residential wiring for branch circuits and general-purpose wiring. Underground feeder, or UF cable, is a type of cable that is designed for direct burial in the ground. UF cable is typically used for underground circuits, such as those that supply power to outdoor lighting or equipment. The NEC specifies detailed requirements for each wiring method, including the types of conductors that are permitted, the support requirements, and the grounding requirements. It's important to select the appropriate wiring method for the application and to follow all applicable codes and safety precautions when installing electrical wiring. Voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Voltage drop can cause problems with electrical equipment, such as reduced lighting output, motor malfunction, and equipment overheating. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it's important to use conductors of adequate size. The larger the conductor, the lower the resistance and the lower the voltage drop. The length of the conductor also affects voltage drop. The longer the conductor, the greater the voltage drop. To reduce voltage drop, it's important to keep conductor lengths as short as possible. The load and the circuit also affects voltage drop. The higher the load, the greater the voltage drop. To reduce voltage drop, it's important to avoid overloading circuits. Voltage drop can be calculated using various formulas and calculators. These tools take into account the conductor size, length, load, and other factors to determine the voltage drop in a circuit. It's important to calculate voltage drop before installing electrical wiring to ensure that it meets the NEC recommendations. The NEC provides tables and guidelines for calculating voltage drop in different types of circuits. These resources can be helpful in selecting the appropriate conductor size and minimizing voltage drop. Harmonics are distortions of the sinusoidal waveform of alternating current. Harmonics can be caused by nonlinear lows, such as electronic devices, variable frequency drives, and uninterruptible power supplies. Harmonics can cause various problems in electrical systems, including overheating of equipment, increased energy consumption, and interference with communication systems. To mitigate harmonics, various techniques can be used, such as harmonic filters, reactors, and transformers. Harmonic filters are designed to block or reduce the flow of harmonic currents. Reactors are used to smooth out the current waveform and reduce harmonic distortion. Transformers can be designed to block or reduce the flow of harmonic currents. Harmonic analysis is the process of measuring and analyzing harmonic distortion in an electrical system. Harmonic analysis can help identify the sources of harmonics and determine the appropriate mitigation techniques. Harmonic analysis is typically performed using specialized equipment such as harmonic analyzers and power quality meters. The NEC provides guidelines for addressing harmonics in electrical systems. These guidelines include recommendations for harmonic mitigation and for the design of electrical systems that are less susceptible to harmonic distortion. Power quality refers to the characteristics of the electrical power supply, including voltage, current, frequency, and waveform. Poor power quality can cause various problems with electrical equipment, such as malfunction, damage, and reduced lifespan. Common power quality problems include voltage sags, voltage swells, voltage transients, harmonics, and flicker. Voltage sags are temporary reductions in voltage that can be caused by motor starting, equipment switching, or faults on the power system. Voltage swells are temporary increases in voltage that can be caused by capacitor switching or lightning strikes. Voltage transients are short-duration high-voltage spikes that can be caused by lightning strikes, switching surges, or electrostatic discharge. Harmonics are distortions of the sinusoidal waveform of alternating current, as discussed previously. Flicker is a rapid fluctuation in voltage that can cause lights to flicker and can be annoying or even harmful to people. To improve power quality, various techniques can be used, such as surge suppressors, voltage regulators, harmonic filters, and uninterruptible power supplies. Surge suppressors are designed to protect electrical equipment from voltage transients. Voltage regulators are used to maintain a constant voltage level, even when the input voltage varies. Harmonic filters are designed to block or reduce the flow of harmonic currents. Uninterruptible power supplies, or UPS, provide backup power in the event of a power outage, protecting sensitive equipment from voltage sags and other power quality problems. Power quality monitoring is the process of measuring and analyzing power quality parameters in an electrical system. Power quality monitoring can help identify power quality problems and determine the appropriate mitigation techniques. Power quality monitoring is typically performed using specialized equipment, such as power quality meters and data loggers. The NEC provides guidelines for addressing power quality problems in electrical systems. These guidelines include recommendations for power quality mitigation and for the design of electrical systems that are less susceptible to power quality problems. Motor control circuits are used to start, stop, and control electric motors. Motor control circuits typically include components such as push buttons, switches, relays, contactors, and motor starters. Push buttons and switches are used to initiate motor start and stop commands. Relays are used to control other components in the circuit, such as contactors and motor starters. Contactors are electromechanical devices that are used to switch large currents, such as those required to start and run electric motors. Motor starters are devices that provide overload protection for electric motors. Motor control circuits can be simple or complex, depending on the application. Simple motor control circuits may only provide basic start and stop functionality, while more complex motor control circuits may provide advanced features such as speed control, reversing, and jogging. The NEC specifies detailed requirements for motor control circuits, including the types of components that are permitted, the wiring methods, and the overcurrent protection requirements. It's important to follow all applicable codes and safety precautions when installing or working on motor control circuits. Programmable logic controllers, or PLCs, are industrial computers that are used to automate industrial processes. PLC are used in a wide variety of applications, such as manufacturing, process control, and building automation. PLC are programmed using specialized programming languages, such as ladder logic, function block diagrams, and structured text. PLC can be used to control a wide variety of devices, such as motors, valves, pumps, and sensors. PLC offers several advantages over traditional relay-based control systems, including increased flexibility, improved reliability, and reduced wiring costs. PLC can be easily reprogrammed to accommodate changes in the process, and they can be networked together to create distributed control systems. The NEC provides guidelines for the installation and wiring of PLC in industrial environments. These guidelines include recommendations for grounding, bonding, and overcurrent protection. Grounding electrode systems consist of grounding electrodes and the conductors that connect them to the electrical system. The purpose of the grounding electrode system is to provide a low impedance path to ground for fault current, which helps to protect people and equipment from electrical shock and fire. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Ground plates are typically made of copper or steel and are buried in the ground. Metal water pipes can be used as grounding electrodes if they meet certain requirements, such as being electrically continuous and in direct contact with the earth for a minimum of 10 feet. The NEC also specifies the size and type of grounding electrode conductors that are used to connect the grounding electrodes to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Bonding jumpers are used to connect different metal parts of the electrical system together to ensure that they are at the same electrical potential. Bonding jumpers are used to bond metal enclosures, conduit, and other metal parts to the grounding system. The NEC specifies the size and type of bonding jumpers that are used in different applications. Separately derived systems are electrical systems that receive power from a source other than the utility grid. Examples of separately derived systems include generators, transformers, and solar photovoltaic systems. The NEC specifies requirements for the grounding and bonding of separately derived systems. These requirements are designed to ensure that the separately derived system is properly grounded and bonded to protect people and equipment from electrical shock and fire. Transient voltage surge suppressors, or TVSS, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can be caused by lightning strikes, switching surges, or other events. TVSSs work by diverting the surge current to ground, preventing it from damaging sensitive electrical equipment. TVSSs were typically installed at the service entrance of a building or at individual electrical panels. The NEC provides guidelines for the installation and wiring of TVSSs. These guidelines include recommendations for grounding, bonding, and overcurrent protection. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from transient voltage surges and other power quality problems. SPD are similar to TVSSs, but they offer more comprehensive protection against a wider range of power quality disturbances. SPD are typically installed at the service entrance of a building or at individual electrical panels. The NEC provides guidelines for the installation and wiring of SPD. These guidelines include recommendations for grounding, bonding, and overcurrent protection.